In this video, I'm going to talk about different ways of representing waves using displacement time graphs and displacement distance graphs. It's important to note before we start that both longitudinal and transverse waves can be represented with both types of graph, but you won't be able to know what type of wave you have when you draw the graph itself. So a graph of a transverse wave will look exactly like a graph of a longitudinal wave in terms of displacement time graphs and displacement distance graphs. So it's important to read questions carefully so you know what type of wave you're dealing with and what the direction of the displacement of the particles will be in, left and right for a longitudinal wave and up and down for a transverse wave. Okay, so the first type of wave I'm going to talk about is a the first type of graph I'm going to talk about is a displacement time graph. Okay, and a displacement time graph shows what a single particle in the wave is doing throughout the time period measured. Okay, so in this case I have two graphs here at the bottom. I have one for ball number 1 and one for ball number 7. Notice that ball number 1 and ball number 7 have different graphs. That's because the displacement of these two balls is different during each time. So when ball number 1 is going up, ball number 7 is going down, and vice versa. Displacement time graphs are useful in making a few measurements. So if I were to measure peak to peak, so I measure the peak to the other peak of my displacement time graph, I can find the period of my wave. So how long it takes to complete one oscillation would be peak to peak on a displacement time graph. The other thing that I can measure on a displacement time graph is the maximum displacement of my particles, which is the amplitude. So I can measure the amplitude by measuring the distance from the rest position, black line here, sometimes called the equilibrium position, and the peak of the wave. The next type of graph that we're going to talk about is a displacement distance graph, or a displacement position graph. In this graph, I like to think of it as if I were to take a snapshot of a wave at a specific time, that's the way the wave would look at that specific time. And so the way a displacement distance graph is created is we look at the displacement of each particle in the wave at a single time. So I can see when I look at time 1, if I draw my dotted line straight down, my ball in this position has 0 displacement. Look at ball number 2, my ball in this position is displaced to the right, so I have a positive displacement. Ball number 3 is displaced even more, so we're continuing to go up. Ball number 4 is placed to a maximum, so that's why at this position I have my amplitude, and so on and so forth. And so it's like taking a snapshot of the wave. The displacement distance graph is going to be useful for measuring a few things, just like the displacement time graph. So if I were to measure the length of one oscillation in my displacement distance graph from here to here in this image, okay, that's going to be my wavelength, lambda. Okay, and just like my displacement time graph, my displacement distance graph can also be used to find the amplitude of my wave. If I measure from the equilibrium position to the peak, I can find the amplitude. One of the skills you might need to demonstrate using a displacement distance graph is the ability to find the location of the rarefactions and the compressions of a longitudinal wave. So if I look at my graph above, I can see that I've drawn lines indicating the direction at which different points of the wave are moving. So if we look at the left-hand side of the graph, right here, we see that all the wave particles at this position are being pushed forward. If we look at this region of the graph, we see that all of the wave particles are being pushed backward, and they're all converging at this point right here on 2. Okay? Because the wave particles are pushing forward at this point and backward at this point, we're going to have a compression. So all my waves particles are being pushed all into one place. Okay? You can notice a compression without having these nice beautiful red arrows drawn for you. by just remembering that the compression, the center of the compression, can be found at the most negative slope, or where the slope of the graph is at its most negative. Okay, so if we wanted to find a rarefaction, we can use a similar system. So if I switch to green. So if I look at the part of the graph where my particles are being pulled apart, so I see that this region of the graph, particles are all being pulled right. At this region of the graph, all the particles are being pulled left. And so all the particles are being pulled apart at this point here, which converges around 4. Okay? And we see that this is the point in the graph where the slope is the most positive. And so we could say that the rarefaction can be found at the point on the graph where the slope is the most positive. And if you're able to identify the compressions and the rarefactions of a longitudinal wave, remember from before that two compressions are in the same phase, and therefore the distance between two compressions is one wavelength. And therefore you could use the same thinking for rarefaction. The distance between two rarefactions would also be in phase, and therefore the distance between them is one wavelength.